go ahead and get started. Any questions or anything about anything? And so you can give it to me later, whatever, if you have homeworks or labs, just feel free to bring those to the front. So everything moving smoothly so far, feeling good about things. Cool. All right, so now chapter 3, we're going to be going into chemical bonds. So chapter 2, we kind of saw electrons, how to fill them in, but now we're going to be looking at how do those electrons interact, and then also naming those compounds. And so we said that compounds are composed of atoms held together by chemical bonds. And so chemical bonds just result from the attractions between the charged particles. And so we'll kind of see how bonding is a spectrum from anywhere from shared bonding, so to atoms sharing electrons, and all the way to where you have a charge transfer situation. And so there's 3 main types. We're mainly going to be focusing on ionic and covalent. So ionic, again, that's just metal plus nonmetal. Anytime you see that. And again, you're going to have a whole transfer of electrons. So they're not sharing any. It's, again, our alkali metals give up an electron and give it to a halogen, chlorine, fluorine. And then covalent, so that's usually nonmetal plus nonmetal. And again, this will be sharing electrons. And then metallic we don't really talk about, so this is kind of a special type of bonding, and this is more for like metals. And so metals differ in that they're considered more of a sea of electrons, and so they're just kind of delocalized electron systems, so we won't really discuss that. All right, so now let's focus on ionic versus covalent. And so taking a closer look at table salt. And so, of course, observe some of the characteristics of table salt. This will be something you'll be doing in lab as well. Just looking at chemicals, what do they look like? So you can see it crystallizes in kind of these squarish looking shapes. And then if we take a look at the molecular structure, we see, again, it's just repeating units of sodium and chlorine. And to take note of the size difference, too. So sodium, it's small. And so part of that is because it's going to lose an electron, so it's losing that outermost valence electron. And so now it's kind of one shell smaller. And so that's what makes it tiny. Meanwhile, chlorine, so we didn't add anything to its shell. We're just filling up that p orbital. So kind of reminding ourselves. So from last time, right, these all had NP5, and then we would just fill in an electron to make chlorine P6. So that'd be 3P6. So it'd be filled, but of course, right, if we're thinking about the nucleus, so the nucleus still only has 17, right? This is not a good periodic table. So the nucleus still has 17 protons in there. So if we add electron number 18, so now it can't be held as tightly since you have more electrons than you have protons in the center, kind of drawing it to it. And so with that, chlorine's radius is larger. And so you'll notice that in a pattern. So anions always have a small radius, and anions have a large radius. And again, you can see them just repeating in our crystal lattice structure. And so meanwhile, ice, and so ice is unique in that it occupies more space than the liquid form. So the solid form takes up more space, and that is because the water molecules orient themselves to make our solid structure. This is not a good depiction. of the solid state structure. But it has a solid state structure, and the difference, of course, being that we have discrete molecules of H2O versus just a repeating pattern.
You said cations have larger radius?
Smaller. So cations are always small. So anytime you see that positive charge, that's a cation, so it's going to have a small radius, and the anions have a large radius. This is not the best picture of water, but I just wanted to give somewhat of a depiction because it takes more of this spread out form in a rigid structure, so that's why it occupies more space. And so taking a closer look at our ionic bonds, so again, this is between our metal atom and our nonmetal atom, and they involve a transfer of electrons from one atom to another. And so the metal atom will usually lose an electron to become a cation. So it loses electron. And again, that's sodium, potassium, calcium, any of those are good examples, aluminum 3+. And the nonmetal atoms, now the nonmetal is accepting those electrons, and it becomes the anion. So that means it would have to have gained an electron. So bromine, sulfur, fluorine, oxygen, phosphide, any sort of those. All right, so let's take a look at sodium chloride. And so this is where we can practice drawing our Lewis dot structures as well. So we can start with our Lewis dot structure of neutral sodium. So there's our sodium metal. Then we'll go ahead and draw chlorine. And so how many valence electrons does chlorine have? 7. So 7, exactly, so good. I don't remember if we explicitly covered that, and that might be something you want to write on your periodic table. Is you could do valence electrons, so this has 1 valence electron, 2 for group 2, and they should match with the groups. And so this is group 3, so 3 valence electrons, 4 valence, 5, 6. So everything in this group has 7, just like you said. Hint, hint, it will come up on your quiz, and 8 valence electrons for that one. All right, so now we have our 2 neutral atoms. And so now they're going to do their reaction. And so that means sodium is going to give up its electron to chlorine. And so we can kind of draw our product. So that's going to leave us with sodium cation. And so we can draw its new Lewis dot structure. So now it has no more valence electrons since it gave it up. And now chlorine becomes our chloride. And now it is satisfied by the octet rule. And of course it has that negative charge on it. And so now we can just leave it like this in this little depiction. So again, showing our transfer of electron from our sodium to our chlorine. And of course, the other thing that you probably noticed is we made something positive, something negative, and so that's the only thing that's holding those atoms together. So these oppositely charged ions attract one another by electrostatic forces and form an ionic bond. And so the result is, again, this lattice structure, which is just whatever 3D array your cations and anions fall in. And so different compounds have different structures, but we won't go into those details. So again, here's just another depiction. We started with neutral sodium, neutral chlorine, and then the electron, of course, moving from sodium to chlorine. And again, showing how radically these properties can change. So you take something, two substances that you would not want to eat, that would be extremely toxic. You know, there's no way you could try to digest sodium metal, it'd be exploding in your mouth, and be extremely alkaline too. Chlorine gas, I'm sure that would like immediately poison you. But then put the two together, and we get table salt, which you do consume every day, I presume. And so again, with this Lewis theory, we can combine both our electron configuration, our Lewis dot structure, and it gives us a lot of information. And so again, this Lewis model, it's mainly used to illustrate covalent bonded molecular compounds, but we can also use it, again, showing our sodium chloride and our ions. And so the other thing we want to be able to do is identify our valence electrons. So anytime we see these electron configurations, so looking at potassium, so just follow along, 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. We can glance at our periodic table, and that matches what we would get. So 4s, good. And then so we can identify our 4s1 as our valence electron. So again, that's where all the action is occurring. This is what dictates its reactivity. And then for K plus, our cation, of course we've lost an electron, and then we can write our new electron configuration. And then it's just emphasizing, so now this would be the octet in our previous levels, so we could say it's satisfied by the octet rule. And now these would also be considered the new valence electrons for potassium plus. And so now this table just tries to emphasize which ions have just one sort of oxidation state. So again, we've seen a lot of the alkali metals, the alkali earth. There's all of them with the +1 oxidation state for the alkali metals, +2 for the alkaline earth. And then scandium, yttrium, so they tend to always be in the +3, so they went ahead and labeled them there. Aluminum is 3+. I would have added zinc in there, and silver. So those are also common. So zinc should always be in the 2+, silver in the 1+. And then over on the right side, we have all our nonmetals, and of course these would later become our anions in an ionic compound. And so group 7, again, they're all -1 for the oxidation state. Group 6, -2, then group 5, -3. And so again, like we've been saying, these ionic compounds are composed of cations and anions. And so these are just some examples. So we'll get into what these mean. So all these are polyatomics. And what we'll later discover is, so for example, this carbonate, this is covalently held together. And carbonate has a 2- charge, but I'll hand out a little cheat sheet for that. And so this is covalently bonded, but then the aluminum and the carbonate would be held together just by an ionic bond, so just by electrostatic forces. And so same thing with these other polyatomics. So HPO4 is all one thing held together covalently, but calcium and this group are all held together again by ionic bonds, so magnesium. And this is called sulfate. So again, sulfate is held together covalently, magnesium and sulfate ionically. And I think we've already emphasized this, but we'll say it again. So again, the basic unit of an ionic compound is our formula unit and is the smallest electrically neutral collection of ions. And we've been kind of getting a taste for this as we practice writing formulas a little bit and started to. So again, that's why we have 1 sodium, 1 chlorine, and that's a +1 oxidation state, chlorine's -1, and so they're balanced in a 1-to-1 ratio. And so just to summarize, so ionic compounds always have a positive and negative ions. The chemical formula, the sum of the charges of the positive ions must equal the sum of the charges of the negative ions. And again, this is always assuming that this is a neutral formula. Of course, you could be given a charged compound, then you want to equal the charge. And then that formula of the ionic compound reflects the smallest whole number ratio. So more examples, magnesium fluoride. And right, we knew magnesium was in the 2+ oxidation state. Fluorine is in the -1. You do a little swap trick, then that gives you your formula. Magnesium fluoride, you can balance it by charges as well, any which way. Or let's see, aluminum bromide. So again, balanced with aluminum being in the 3+ oxidation state, bromine's -1, so we need 3 bromines to balance out that 3+ charge. All right, so now let's get into writing the names of all these ionic compounds. So we have 2 different categories of ionic compounds. So we have ionic compounds, so they're all metal plus nonmetals, but then we have metals that form only one type of ion. And so this is going to be the alkali metals like we've been talking about, the alkaline earth, and then I mentioned zinc, aluminum, and silver. So all those, if you see them in a compound, they always have one oxidation state, and we'll go over how to name them. And then the second one only varies in that they usually involve the transition metals or inner transition, so that's just the F block. So anytime you have an F block, and then these P block metals, so that's going to be tin and lead, tend to be the 2 most common ones, and probably indium and tellurium. But any of those kind of funky bottom ones, you're going to have to indicate the oxidation state because there could be different types. All right. And so how we name them, for the first type, so when we just have a metal that we always know the oxidation state in, we just have to name the metal. So that's going to be your cation. So the name of the metal plus now the nonmetal, except you change the ending to "ide." So let's practice some of these. So how would you name NaCl? So sodium chloride. Good. Let's try the next one. Magnesium oxide. This one. What did you say, calcium fluoride? Excellent. Calcium fluoride. And what about this last one? Aluminum oxide. All right, so burn that into your brain. So that's fairly straightforward. And so now this periodic table attempts to kind of show you your variable oxidation states. You also have your periodic table, which helps you, but not because, like, you know, let's just look at manganese. What does your periodic table say for oxidation states?
7, 4, and 2.
So at least that one has 7, because they don't always list them. But, so there we have 7, 4, 2, and it could also be other states that aren't listed. So you could have like magnesium 1, same with like nickel. So nickel can also take 1 and 3, so not just 2. Cobalt likes to be in all sorts of oxidation states, anywhere from like 1 to 6 potentially. And so all these we'll have to name differently. So we have mercury as well. Mercury is funny. I'll point out mercury, since you have mercury in the 2+ oxidation state, that's just Hg 2+. But then you might find it in the 1+ oxidation state, and it's Hg 2, 2+.
And when you say oxidation state, it's just the difference in the electrons, right?
Yeah, so just,
And the valence electrons.
yeah, so the oxidation state, like, that would just be how many electrons it lost, basically. And, yeah, so if you're trying to determine it, it'd be like how many it has versus minus how many it currently has, but usually you see how many electrons it lost, or you're looking at like the compound. And so now let's do some practice with these, they're called multivalent metals. And so metals in this category tend to have multiple charges, so multiple oxidation states. And so their charge cannot be predicted, and it has to be noted in their name. So you can't just say, for example, iron oxide. So there's 2 different iron oxides. And so let's look at this example. So iron forms a 2+ cation in some of its compounds and a 3+ cation in others. And again, this is just most common. And so now you have this problem of FeSO4 and Fe2SO43. So now how do you know? So let's break it down, and let me go ahead and hand you this polyatomic sheet, since they use the polyatomic example. All right, so let's start with looking at our sheet. So kind of, we're here. So we're trying to compare FeSO4 versus Fe2, SO43. And so normally you would just be given this and then kind of determine the oxidation state. And so what you have to do is you have to use clues. So who is it bound to? And you look at the anion for these multivalent metals, and you determine, well, what oxidation state is the anion in? And since we're dealing with a polyatomic, so go ahead and try to find your polyatomic. So where's sulfate on there? And then what charge does sulfate have? -2. So it's down here at the bottom, if you didn't locate it. So sulfate. So sulfate and SO4, 2-. And so, again, this all means, and I can draw out the structure for you. So this is what sulfate would look like. and you will get here shortly in a chapter or two how to draw this. So this is, again, all covalently bonded. This overall has a charge of 2 minus. So there's our 2 minus charge. And so now if we're examining our formula, so I'm going to just put a 2 minus here. They're in a 1-to-1 ratio. So what oxidation state must the iron be in this FeSO4 here? You can show me fingers too.
With the charge or the?
Yeah, so what's the charge on the iron then to make it
-2?
-2 or?
Or just 2, right?
Yeah, well, +2.
Yeah, positive.
Yeah, so if this is -2, right, we have to make our neutral compound, so our iron has to be 2+.
Oh, so they found the electrons are bonding.
Yeah, well, they're not only bonding, but they're like have to be held together in an electrically neutral ratio. And so now we can write the name of this compound. So we would write it iron. And then the oxidation state has to be noted in their name. So you want to write metal. Then there's going to be a Roman numeral for the oxidation state. And then you'll do your ending. And either that "ide," or in this case, since we have a polyatomic, we'll just name the polyatomic. So in this case, it's going to be iron 2 sulfate. Yeah.
So when you're doing the drop and swap in the numbers at the bottom, do you also swap the charge of both elements when you're putting together the compound?
Yeah, so I think I kind of know what you're asking, because we could do the swap trick, and correct me if I'm like on the wrong path, because what you could do is what I sometimes tell people you could do the reverse swap trick. And so that means, well, if they have a coefficient of 1, right, then you can back it out. Then you get 1 plus 1 minus, right? But then you'd want to check yourself. So then you'd stop and check, well, does this -1 match with sulfate? And so what's the answer? So no, but then you could just multiply everything by whatever factor it's off by. So in this case, if it's by 2, multiply it by 2. So this times 2, this times 2. And now that kind of reverse swap trick works. Did that clarify what you're saying?
Yeah, no.
And the swap trick probably works better in this case when they're like funky numbers. And so if we put our oxidation state, so -2 for our sulfate, and so notice how that kind of matches. And so mathematically, what's the oxidation state of iron? So if you're doing the reverse swap trick, then you're going to take these and reverse them. You can also set up your algebra. So this is electrically neutral. And then 2 for iron times just whatever Fe oxidation state plus sulfate. So that's 3 times -2. So then you get 2 times my oxidation state of iron plus -6 equals 0. So what does X have to be? So it should be +3. So you should get 6 equals 2x. And so X equals 3. What was it? So did we follow the algebra? I hear some questions. You just have to follow the algebra. So you should get +3, but that's what I was saying. Use your reverse swap trick because it works, right? So our subscripts were here, and so if we reverse them, they matched up. That's a little bit easier than maybe doing the algebra for some people. But then again, double check yourself. So -2, we have 3 of them, so -2 times 3 is -6. And then if this is 3 plus, so 3 times 2 is +6. So 6 plus -6 gives you back to 0. So do we all follow on that one? So then it would be iron 3 sulfate. And so again, for these, what they like to call type 2 binary ionic compounds, aka metals with variable oxidation states. Again, we put our oxidation state in parentheses. So there's 2 oxidation states of copper that are most common. So you can say copper 2 versus copper 1. So you have copper 2 chloride and copper 1 chloride. So if we wrote copper 2 chloride versus copper 1 chloride. So what would my formula be for copper 2 chloride? You can do your little swap trick too. So what's the formula for copper 2 chloride? So I know I have a Cu and a Cl. But then if this is 2 plus, and then what's the oxidation state of chlorine? One or -1. So then if we do the little swap trick, what would we get for our formula? So CuCl2. And then, so what about for copper 1 chloride then? What would the formula be? So CuCl. And again, you could do your little swap trick. So 1 plus, 1 minus, and that gives you 1 and 1. So of course we don't have to write anything. And so here's another example. So we have copper 1 oxide versus copper 2 oxide. And this time they wrote out the formulas. But again, let's just practice. So copper 1 oxide, so CuO, so 1 plus versus a 2 minus. So you could do your swap trick, and that gives you Cu2O, just like they did here. And then so for copper 2 oxide, do the same thing. Of course, if you do the swap trick, you would get Cu2O2, but then we want it in the smallest whole number ratio, so that brings us back to CuO. Or of course, you could always just recognize this is 2 plus, 2 minus, 1-to-1 ratio.
So when you have, like something 2, you can cancel that out?
Yeah, so if you ended up like this, and this usually happens in like ionic compounds or some other weird stuff. We'll look at other scenarios, like tin. If you do the swap trick, you can get some funny stuff, but you just kind of watch out. And so this is more of like a fun fact / aside thing. And so why I mention it is, especially if you look at older textbooks, they used to be named differently, and actually I learned a completely different system of chemistry, even though I didn't learn chemistry that long ago. Of course, it gets longer every year. But if you notice, so there's kind of two most common oxidation states for most of these metals, and the one with the lower oxidation state takes the OS form, and the higher number takes the IC. So if you see like chromous in a textbook or in like an old chemical bottle, that just refers to chromium 2+, versus chromic, so that's chromium 3+. So iron has ferrous and ferric. Same thing with cobalt, so you see cobaltous versus cobaltic. And it goes on, so tin, so stannous versus stannic, lead, plumbous versus plumbic. But lucky for y'all, we don't use this anymore, so I don't expect this. And so it's much easier to use the Roman numerals. Plus, these names don't account for all the oxidation states you might encounter. But just, again, be aware of it. If you see it, you'll know what they're talking about. So let's try some more naming. So I'll give y'all, take 5 minutes or so, ask your neighbor, and try to name these 4 compounds here. let's go over them. Oh, but before I forget, I want to give a big shout out to you guys. So everyone had turned in a lab and a quiz last week, so I was really proud of y'all. So give a big hand to your class and keep up the work. So right now y'all are rocking it. All right, what do we get for FeCl2 here? So iron 2 chloride. Any questions about this? So you could probably just back it out with your swap trick, and that kind of worked for that one. What about this one? Iron 3 chloride, excellent. Again, our swap or reverse swap trick works pretty well. So that matches. And then what about this one? So you fell into the trap just a little bit. So if you did the reverse swap trick, you do get 2 here, but what's the problem with oxygen? What's its oxidation state? -2. And so again, this is fine, but just take this, now multiply everything by 2. So -2 plus 4. So what's our oxidation state for tin? This number? 4, yeah. So tin, 4 oxide. All right, so let's just recap what we did. So if you do the reverse swap trick, so that's fine. You get 2 plus -1. But then this is where you check, because your oxygen is kind of like your sanity point. So oxygen should always be -2. And then we go, uh-oh, okay, it's not -2. Multiply everything by that factor. Now we have oxygen is -2. That means tin is +4. So that works. If you're confused by that, there's always the good old algebra method. So just set up overall 0. We have tin, whatever its oxidation state is, plus 2 times -2 for oxygen. So you get 0 equals x plus -4, so 4 equals x. So again, whatever way is easier. And that's why I said that warning about tin, because sometimes it will be one to give you odd ones, so tin and lead. And then this last one, CON, how would you name it? Except what's missing? So cobalt nitride. What oxidation state is cobalt though? So you got to base it off the nitrogen. So you could, so if you did the swap trick, right, where you get +1 and -1, except what's the charge on nitrogen usually? So it's 3 or -3. So then we'd have to multiply everything times 3 to give us cobalt 3 plus and nitrogen 3 minus. So that matches with what it is. So what's our oxidation state of cobalt? So cobalt 3 nitride. And again, for this one, there's also the algebra. So 0 is equal to cobalt plus our nitrogen, which is -3. So 3 equals x. And so now we'll go into naming polyatomics. And so again, with these naming the polyatomics, it's essentially familiarizing yourself with these polyatomics. And so I'll just point out at least a few that come up a lot. So hydroxide, we'll see that. So for example, KOH is a common compound we use, so that would be potassium. And to notice you name them, you just name either the appropriate metal cation, or if it's an anion, since we do have ammonia. So if you look at your chart, ammonium, NH4 positive, that is one of the few polyatomic cations you have. And so in that case, you would just name that cation and then the appropriate anion. And so again, this would be potassium, and then we just name the polyatomic, so hydroxide. Let's see, carbonate also comes up a lot, so I'll highlight this. So, for example, calcium carbonate, and again, I write the formula balance, so carbonate has an overall 2- charge, calcium's 2+, and they're in that 1-to-1 ratio balanced, so that's fine. Let's see, sulfate is also another ion that's used a lot. So for example, sodium sulfate, so this would be Na2, SO4, so we need 2 equivalents of sodium to balance out that 2- charge. Now, acetate, it does come up a lot, maybe not so much in this chapter, but you'll see it again in the acid-base chapter. And the only reason why I point it out is because it's confusing and throws people off, because you can also see it written like this, CH3COO. And so, for example, sodium acetate, you might see something written like this, and it might be in another order too. But anytime you start seeing like carbons in a polyatomic, at least check it for acetate or oxalate or something organic-y. So just watch for that. Nitrate comes up a lot. It's another common one, like potassium nitrate, or I think metal salts, so copper nitrate you'll use as well in lab. There's good old ammonium. So again, it's unique in that it's a cation. So ammonium chloride is a good example. So NH4Cl, again written balance. So ammonium has an overall +1 charge, so I just put 1 chlorine there to balance it. Then another common one, phosphate. So you'll see phosphate. So phosphate's unique in that it's a 3- charge, so sodium phosphate, you would need 3 sodiums to balance out that PO4. And then of course the rest you can read for yourself. And I believe this is a more extensive list. I can't promise that every polyatomic on there, but at least a lot of them are. All right, so now take a couple of minutes again and see if you can name these. So you have to do some hunting potentially. So take a couple of minutes and then we'll go over them. So again, ask your neighbor. So what do we get for the first one? Potassium dichromate. Excellent. So that one wasn't too bad. You just had to find the Cr2O7 on the periodic table, or not the periodic table, on your polyatomic sheet. Excellent. What about the next one? MgOH with the 2. What do we get for this one? Magnesium hydroxide. And then what about this last one? It's a little tricky. So I like that, but what is it missing? So what? Yeah, so we got to indicate the oxidation state, and so you had to find nitrate. So if you found it on your polyatomic sheet, so where is it? So nitrate, you saw that it was NO3 with a little negative charge on it. And so there are 3 of them. And so -3 times 3 is -3. So that must mean that iron is in the 3+ oxidation state. You could also, looks like the reverse swap trick also works. So reverse it, 3 and 1. And so that matches that 1, or rather -1 matches with the overall charge of our nitrate. And so iron 3, nitrate. So just, again, don't forget that you have to distinguish these metals with multiple oxidation states just with our Roman numeral. All right. Questions about this so far? So let's look at some other things that can come up. I feel like, is this all that's this chapter? Well, you might have blown through this chapter. I'll have to look at your book to see what else is in there. So something else that comes up are these like aqua compounds. And this means that there are compounds that are complex with water. And so you can indicate, let me find some hemi aqua compounds. There we go. Sorry, I was trying to find. And so the thing with these hydrate compounds, so let's look at one example. Actually, I don't like that. But magnesium sulfate is one. I was trying to find a better picture representation of it, but I guess not. But sometimes you find these compounds. Let's just go back to this one. And so these hydrate compounds are special compounds where they have some equivalent of water that is in their formula. So it's considered like these discrete units then of magnesium sulfate bound to 7 waters in this case. And there are different versions too. And so with these aqua compounds, you would name them, again, just indicating your prefix. I was trying to find a good example of a hemi-aqua compound, but this just means you have half an equivalent of water for every one molecule, so usually it's like a 2-to-1 ratio. But then you could have like mono-aqua compounds. Sesqui is not very common, but that'd be 1.5 molecules of water, and that's just a ratio. But then we have di, tri, tetra, penta, hexa, hepta, octa, nonadeca. Of course, you can continue. And so again, anytime you see this, so if you write MgSO4, and if you want to indicate that it's an aqua compound, you write this little dot here, and then write however many waters are bound to it. So again, we're looking at the hepta aqua, so 7. And then if we want to name it, we would just name the first part normally, so magnesium sulfate, and then we have to name our aqua, so hepta, and then you say hydrate for the M. Here are some, I was trying to find other good examples. There we go. Well, this is very esoteric. That's not what I'm talking about. Yeah, let's see, let's look at another one. And so another common one is nickel. And so the funny thing about the aqua compounds is they change color. And so if you're ever looking at a bottle of compound, you want to see if it says anhydrous, so that means no water. Or if it's a hydrate, so nickel chloride, for example, is available in an anhydrous form, and that would be a yellow powder. And then the hexahydrate is going to be a green powder. And so you could name, so we would have nickel, and so it's nickel 2 chloride, so NiCl2, and then hexa, so 6 H2O, so you could write it that way. And again, we'll write it, so nickel 2 chloride, and then hexahydrate. And so that's also why your bottles, like on the chemistry bottles, they'll sometimes say anhydrous or not, so that you know whether you're getting a version with water attached to it or without water. And then you can always convert the hexahydrate to the anhydrous form. It's just somewhat difficult, so it depends on the compound. There's usually a purification route, but for example, nickel chloride, you can make the anhydrous version if you boil it in a bunch of toluene for a long time using what's called a Dean-Stark apparatus. And so this is a Dean-Stark apparatus. And so basically you're boiling stuff, you're boiling it, and then this little section over here takes the water, and so water is usually more dense than your organic solvent that you're using. And so the water collects here, the organic solvent is on top and makes its way back into the reaction. And some of them even have little stopcocks where if you are doing a lot of distilling and pulling off a lot of water, you could drain this out and keep going. that's how you would do that. And then something else that I just threw in here, because I don't think this gets well covered till a later chapter. And so we have naming acids. And so acids are always funny, and they follow different patterns. So you can have just your simple acids, and such as hydrobromic. So with bromine, so bromide becomes hydrobromic acid. So hydrochloric acid, hydrofluoric acid, hydroiodic acid. And then we also have acids with our polyatomics. So cyanide becomes hydrocyanic acid, so changing the "ide" to "ic." And then with these other ones, so you have nitrite and nitrate. And so the lower oxidation state gives you nitrous acid. So this isn't too common, but we do use a lot of nitric acid, so HNO3. That's commonly used in our lab. So same thing with phosphoric acid. So you can have other versions, but usually you have H3PO4, phosphoric acid. We don't use sulfuric acid a lot, so notice, again, it's the lower oxidation state, so SO3 2-, while SO4 2- sulfate is sulfuric acid. Excuse me. You also have hypochlorous, chlorous, and perchloric acid. So perchloric acid is pretty dangerous, and just because a lot of the perchloric compounds can be explosive. So if you ever wanted to work with perchloric acid, you actually need like a special fume hood that's constantly running water so that you don't have any crystals of perchloric compounds forming, and then that could be bad. All right, I think we covered pretty much everything. Do you want to take just a 10-minute break, and then I'll start you on your quiz early, if that works with you. And then I have homework as well. Do you want me to just pass it out? Okay, let me go ahead. I'll pass out your homework. And I'll give you all a 10-minute break. Do our quiz. Don't forget about your valence electrons. And then I'll give you all the rest of the time to work. Yeah, and then if you want to start a homework pile, I will take anything you have for me.
Yeah, it's just, I mean, I kind of, sort of, you know, kind of remember from last year. Pretty much the lecture. Okay, I didn't get that question, so.
Hopefully cover.
Okay, yeah, I still don't know what that, but.
I rewatched the lecture for a little bit.
Oh, for real?
And I got so much.
Oh, thank you.
I will go ahead and end this recording.